Moment of inertia of a hollow cylinder. So we have a hollow cylinder, we're gonna break it up in two parts, the inner and the outer. The inner would have the smaller radius, little r, and the outer obviously having the bigger r from the center to the end of the cylinder. We're gonna fold it out, the height or the length, as I'll label it, the circumference being 2 pi r, and then dr being the thickness of the unfolding of the cylinder. Then we have inertia equaling the integral from the smaller radius to the bigger radius of the rate r squared time by dm, the change in mass. dm equals rho times dv, dv being the length times area, rho being mass over volume, volume being the length times pi r, but the radius of the cylinder being the bigger radius, the difference of the bigger radius and the smaller radius, you get r squared minus little r squared. Then we take these substitutions in for dm equals rho times 2 pi r length of dr, the circumference, the rho, and the dr. Then we're going to plug this into the integral, which will jump right here to r squared by p times 2 pi rl, which will bring out of the integral with just r cubed dr. Jump back here, we'll integrate r4 over 4 integrated by bigger radius and the smaller radius and the constant outside. Then we're going to expand rho into mass over length times pi over the distance and the radius. Then once we integrate and evaluate from the bigger radius to the smaller radius, we get big R4 over 4 minus little r4 to the fourth. Factor out the 1/4. The 1/4 and the 2 come into half. When rho's expanded, the pi and the L are canceled out, so you're just left with the difference in the radius of the cylinder and the evaluated integral, which gives you r4 minus little r4. Expand, the denominator cancels out, and you end up with 1/2 mass times big R squared plus little r squared, and that is the moment of inertia of a cylinder.